Okay, this is where I left off last time, where we were talking about the atom, about it having a nucleus where the protons and neutrons are at, which is the most massive part of the atom. And then you have the electrons, which are way out there. And they're very, very small, but they take up the majority of the volume of an atom. And at one video that we watched, we saw the guy show an apple, and he said, this is your nucleus, and your electrons would be 1 kilometer away. Okay? So, now we're getting into the idea of what the atom actually kind of looks like. And remember, we can't actually see it, but we can do experiments to figure this out. So, here's Erwin Muller, and you're probably thinking, oh, those look like really pretty pictures. You're right, but these pictures help lead us to the ideal of shells, because the fact is, there's actually a mathematical relationship here among these shells. This is called crystallography. You take a very thin slice of the crystal you're working on, and then you shoot X-rays through it. And then you get these patterns, because crystals are nothing more than regularly shaped patterns. And once we figure out the shape of the crystal, we can then figure out the arrangement of the atoms. Okay, that led us to the idea that there was a shell. And a shell is basically a general region of electron movement around the nucleus. Okay, remember, we can't see the electrons. We can do math to figure out approximately the general probability where they exist. Electrons stay in their area until we excite them. Okay? So when you did your gas emission tubes, and y'all all thought, ooh, pretty light, okay, there was actually a reason for that. I shot electricity through the gas tube. When I shot electricity through there, I excited those electrons, and they started going, woohoo! We got energy now, baby! Here we go, up to the next level, bam! And as it goes up to the next level, it emits light. Okay? So, in spectroscopy, to excite these electrons and get them moving, we've got to provide it with some energy. Because remember, this all goes back to, bam, energy. Law of conservation, energy, and mass. Remember we talked about that? Boom. All right, here it is. So, they stay in the regions until they're excited. Each region is a specific distance away from the nucleus. Orbitals are the paths that the electrons go within the shell. And unlike Bohr's idea, where Bohr said, you know, they run these tracks around the nucleus. I'm sorry, not Bohr. That was Rutherford. Rutherford gave us that they ran these paths, boom, 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 like the solar system. Bohr said, no, man, why would they be running paths? Give me a reason why they're running paths. And Rutherford's like, I spent 2 years on this. They run paths. And Bohr's like, no, man, give me a reason. Come on. Give me a reason why they're running paths. And since Rutherford couldn't give him a good reason, Bohr's like, this is illogical. Why would an electron run a path? Doot, 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 doot. You had to have some kind of force it to run that path. So basically these electrons bounce around in these shells, and they go wherever they want to, but they stay a certain distance away from the other shell and from the nucleus. And so they can go anywhere they want to in this shell. Okay? They're not running paths. And all this came from Erwin Muller photographing the locations of the atoms in the metal crystals. Okay, Wolfgang Pauli. During the early 1900s, we have a whole bunch of scientists that actually they had a meeting and they started talking about this idea of quantum physics. You had big players, Einstein, Schrödinger, Dirac, Wolfgang Pauli, Bohr. I mean, names of impeccable intelligence. Pauli tells us that, you know, when you have this electron, it's spinning, and as it spins, because of what we know about electricity, and if you take a magnet and you spin a magnet, you can produce electricity, which is how generators are made. Electrons are very much like that too. And he said that electrons that spin opposite of one another are attracted to each other, bam, just like magnets are to opposite poles. So, this right here, Pauli's exclusion principle. No more than 2 electrons can occupy the same orbital due to spin. This guy is very, very important. Great short answer question. He's going to be instrumental to electron configuration. All right. Orderly arrangement of electrons. Each atom has 1 or more shells depending upon numbers of protons and electrons. Since orbitals are limiting, there are only a certain number of electrons that can fit into one orbital. All right. I'm going to leave you with this. 1, I want you to think about the periodic table and all that you've learned. What is the maximum capacity of this orbital here? Based on Pauli's exclusion principle. What is true about their spins? Then what I want you to do is I want you to pull up the NOVA app that's on your iPads. And I want you and your group, to practice feeling elements on that periodic table. Okay? All right. I'll talk to you later. Have a great day.